Okay, now it's time and let's start AIP Open Seminar. Welcome to our seminar. We are of Computational Learning Theory team of AIP, and I'm Kohei Hatano, the team leader. First of all, this seminar is you cannot record the seminar. It cannot be reproduced, and the recording of the seminar will be available through the AIP web page later. And if you have any questions, you can use Q&A tab at the bottom or in the menu. Okay, now let's start. So first of all, I'd like to make a very brief introduction of our team. The focus of our team is mainly learning problem with algorithmic challenges. And for example, intersection of discrete and continuous optimization, or learning with structured input or output, which includes computationally hard issues in general. And for example, our projects includes exact optimization of NP-hard scheduling problems using data diagrams, decision diagrams, or boosting algorithm over complex data with zero suppressed decision diagrams. And it fits compress the training data and run boosting algorithm over it. Other example includes online prediction for discrete objects such as permutation or passes, which are applicable for scheduling or ranking. And our approach is based on theoretical computer science point of view, which I mean it focus on worst case analysis or computational resources and so on. There are 3 talks today. Let me introduce them. First talk is about Bandit algorithm for 5G or 6G wireless communication problems. Speaker is Sheriff Hashima. He's a postdoc of our team. Motivation here is that why 5G wireless communication is faster than current Wi-Fi, but cannot pass through the obstacles such as wall or human or etc. While Wi-Fi can. So we need more adaptive strategies to the environment changes. There are actually various communication engineering problems can be formulated as a bandit optimization. That's how bandit techniques comes in. He will introduce several methods or problems. Yes. Then the second talk is about theory and algorithms for Shapelet-Based multiple instance learning. Speaker is Daiki Seihiro of Kyushu University. He's a visiting researcher of our team. The motivation in this topic is that in time classification, patterns called shapelet are quite effective. As you see in this illustration, for example, if you consider leaf classification, then each leaf can be viewed as a time series like this, and some patterns are quite important to classify. This is Shapelet. Many heuristics exist, but there's no good theory for that. He will introduce some theory and based algorithm based on it. Finally, third talk is about include improve the algorithms for online load balancing. Speaker is Yakson Ryu of Kyushu University. He's a PhD student and a part-timer of our team. Motivation here is that online convex optimization is a standard framework for online prediction, but there are some problems that does not seem to fit with online convex optimization framework. Online load balancing problem is one of such examples, but this problem can be formulated as a Blackwell game. This is another tool of online learning and which we are investigating the possibility. He will talk about more about the result. And that's all for my brief introduction. And so please, Sherif, could you start?
My name is Sherif Hashima. I'm postdoc researcher at Kyushu at Riken AIP Computation Learning Theory team. Our talk today is about bandit algorithms for 5G, 6G wireless communication problems. A brief introductory about me. I got my PhD from Ijast University in Egypt, Japan University of Science and Technology. And during I was special researcher at Kyushu University. Then I was special visiting researcher at Kyushu University at 2018. Then I joined Riken AIP as a postdoc since July 2019. Our agenda today, first we have a brief introduction about 5G, 6G problems. Then we will have discuss millimeter waves and problems of millimeter wave. Then we will move to two main problems, which is neighborhood discovery and selection. And we'll evaluate some of multi-armed bandit algorithms, non-contextual and the contextual bandits. Then unmanned aerial vehicle application in disaster area. We have formulated it as a scenario as a multiplayer, multi-armed bandit. Then finally, we have conclusion and future work directions. The milestones of mobile communication, everybody knows that we are now in 5G. Before 1980, it was first generation of mobile, which was applied for voice only. Then second generation, which was GSM, global system mobile for voice and data. Then third G for voice, data, and video. Then 4G is voice, data, video, digital video broadcasting, high definition TVs, video chatting. And then 5G will have a large spectrum, which is millimeter wave from 3 to 300 gigahertz. The bandwidth of the signal will be to up 1 gigahertz. The data rates will be up to 20 gigabit per second. The spectral efficiency will be 30 bit per second per hertz. And the mobility will be applicable to 500 kilometer per hour. And the latency, which is the delay for the signal from the base station to user, and vice versa, it's around half a millisecond. The spectral efficiency is the data rate over the channel bandwidth, and by which we have to measure for how much efficient we utilize the spectrum. The 6G will be launched after 10 years from now, 2013. It will be leveraged to terahertz, and its bandwidth will be larger, up to 3 terahertz. Data rates will be 1 terabit per second. The spectral efficiency will be much higher, 100 bit per second, and the mobility will be 1 kilometer per hour, and the latency will be lower than 1 millisecond. Here, the application of 5G is 4G applications plus video reality, augmented reality, ultra high definition videos, vehicle to everything, IoT, smart cities, wearable devices. While in 6G, we expect to more applications, which will be 3D integrated communication, tactile, and haptic internet, fully automated driving, industrial internet. Now, in 6G, this is the current capacity, and the required capacity is larger. To be sufficient for this required capacity, there is a cube with 3 dimensions, either to utilize the spectrum efficiently using massive MIMO system, non-orthogonal multiple access techniques, spatial modulation, cognitive radio systems, or full duplex systems, which means transmit and receive in the same time by transmitter and receiver, or either use spectrum extension, which our talk today is about millimeter waves that have larger bandwidths, so I can increase the capacity. And also you can densify the network by increase the network from large cells to small cells. So you can use heterogeneous networks or edge mobile computing and caching, or user-centric communication like and also machine-to-machine or vehicle-to-vehicle or device-to-device communications. So the evaluation towards 2020 was to have 1,000-fold of mobile data, 10 to 100-fold of connected devices, and 5-fold of latency, lower latency, and 10 to 100 end user data rates increased, and the power of the batteries will be lower by 10 times. The 5G usage scenarios are enhanced mobile broadband or ultra reliable and low latency communications and massive machine type communications. All of these will be applied for high data rates in gigabit per second, smart homes, smart factories, and smart cities. Also industry automation, automatic industry, and augmented reality, and 3D video, and with ultra high definition screens. Also self-driving cars. Now we will have millimeter waves. It's a portion of the electromagnetic spectrum that is between 30 to 300 gigahertz. And the name of millimeter wave comes from its wavelength because it is in millimeter wave. It's from 10 to 1 millimeter, from 10 to 1 millimeter. And it lies in the electromagnetic spectrum between the microwave and the infrared portion. It have high data rates and high capacity, and narrow beam widths, which have stronger signal to noise ratio, but it have some challenges like high bus loss. It's attenuated because of its short wavelengths and short range transmission. Also high blockage sensitivity. Here, this is the transmitter for the TV of millimeter wave. If this person moves, the transmission will be blocked by the person. And also if this person moves to here, the transmission will be blocked also. So it is sensitive to blocking. And also it's high oxygen absorption. This is the frequency against attenuation. The waves, the millimeter wave, it's attenuated in water and in oxygen. This is the difference between existing mobile spectrum, which is Wi-Fi or 4G. This is the low bandwidth, and this is the millimeter waves with densified cells. This is the vision of how the millimeter wave will help in increasing the capacity of the system by almost 10,000 times. For the spectrum, it will be 20 times, and for performance of massive MIMO systems, it will be 10 times, and for cell decimation, it will be 50 times. So the millimeter wave are expected to be enabler for 100% coverage for all the cells. But we have a problem, which is diffusion and scattering, and also shadowing effect by other persons, and attenuation of these waves by rains and trees, and sensitivity to blocking. So we have to make beamforming, which is aligning the beam of the transmitter and receiver with each other through beamforming training process, which consumes a lot of time and makes overhead data if the number of users is increased. Now there is a strong relation between millimeter wave and device-to-device communication because both have short range. So we could utilize the millimeter wave in device-to-device communications. Here in old system 4G, the base station was supervising the device-to-device setup from the beginning to the end. Here in 5G, The device-to-device setup, it will be by the two devices only, and the base station will get notified by there is a connection or not. The application scenarios of millimeter wave device-to-device communication in vehicular communication and smart environments and disaster management using UAVs, unmanned aerial vehicles, and multicasting if I want to broadcast something from my device to other persons, peer-to-peer and cellular offloading, also mobile gaming and social network and content distribution, which is the same as multicasting. Now we will handle the first problem in our talk today, which is neighbor discovery and selection. We have a central device that wants to connect with the best nearby device, but with considering the blockage of millimeter waves. So in traditional technique, which is conventional technique, this device have to make beamforming training with each of the devices, means brute force or exhaustive search beamforming training. This will increase the time of search and increase the overhead and increase the energy consumption of the devices. So the overall will be a reduction in the average throughput of the network. Also, this process have to be repeated every time because of the dynamic changes in the environment, like blocking and shadowing, which will make it difficult. So our motivation is to solve this problem using the famous multi-armed bandit, which deals with pure exploration dilemma, where an agent is in front of slot machines and he tries to maximize his cumulative reward by investigating the environment that he doesn't know. There is a lot type of multi-armed bandits like single player, multiplayer, stochastic, adversarial, sleeping, and the contextual multi-armed bandit. All of these enhanced us to leverage bandits to our communication problem because it's online learning and sequential decision making, which is much better than deep learning methods that consumes time, offline training, and complexity and time complexity. Now we will handle our first problem, which is neighborhood discovery using multi-armed bandits, non-contextual bandits. Our motivation is to solve the neighborhood discovery of millimeter waves that consumes much more time and large overhead because of the beamforming training process. We leverage the bandits. We made these bandits energy aware, which budget constrained multi-armed bandit like energy most minimax optimal stochastic strategy and UCB upper confidence bound and KLE UCB and Thompson sampling. In this scenario, we are very close to our real scenario where the device battery consumption is taken into account. Our utilized system model, we have a small 5G macro cell or picocell, which is in a stadium or in a traffic light. And there is a central device wants to extend or to establish device-to-device communication. So he's searching about which best device he have to connect. Now the player is the central device and the arms of the bandit are the nearby devices. And the environment is the millimeter wave, which is severe blockage environment. Here we have some assumptions that the devices are quasi-static, which is the same as motion with the slow motion or human motion. And the player positions are known using GPS service, but the millimeter wave blockage is random and unknown. What is the reward here? Our reward is the throughput that is obtained from the nearby device. And the throughput is defined as this equation. Here B is the millimeter wave bandwidth. T data is the time for transmitting data. And gamma K of T is the spectral efficiency. It's log to 1 plus signal to noise ratio. And here N of T is the number of neighbors that do beamforming training. For example, if for conventional search, the all devices will make beamforming training, so this number will be large and the throughput will be low. And this is TBT is the beamforming training time, and T data is the data transmission time. The millimeter wave blockage here, we assume the blocked object like cylinders and positions use random using random two-dimensional homogeneous Poisson point process. So the received millimeter wave received power at receiver will be equal to the transmitted power multiplied by the transmitting and receiving beamforming gains multiplied by line of sight plus null line of sight. The line of sight is the direct communication between the device, transmitter and receiver, and the null line of sight is the reflection due to blocked objects. Here, the blocked object is Bernoulli random variables. This is the equation of line of sight blockage. This is D is the distance between the transmitter and the receiver. Delta is by this equation. R is a blocked object radius, and lambda is a blocking density, and omega is a blocked object thinning factor. Now, as a problem formulation of millimeter wave device-to-device neighborhood discovery, we are targeting to at every trial T, we want to maximize the throughput between the two devices, subject to the remaining energy of the nearby device K will be larger than threshold energy, because simply if your battery of mobile is 1% or 10%, you will not make a device-to-device communication. You will utilize your battery for energy saving and for main communications. So the map protocol here, every round T, the algorithm will choose a device, and the reward are identically independently distributed. Then the reward is revealed to the algorithm. And also the budget constraint scenario will be assumed. Here, the energy aware MOS algorithm, the inputs is the threshold of the devices and the energy for all devices. Then we pull an arm or device one and update its remaining energy by this equation. BTX is the transmitted power, L data is the length of the data to be transmitted, B is the bandwidth, and gamma is the throughput for this device. And we did modify the MOS algorithm by adding a new term that reflect the budget constraint, which is here the dk over ek of t. Dk is the distance between the two devices, and the ek is the remaining energy. We did the same for UCB, UCBV, UCB tuned algorithms made by Euler 2002 by adding this term to explore or to make budget constraint and energy aware neighborhood discovery algorithms. And also for KLUCB by Kabe 2011. Here we used Gaussian distribution type or Gaussian distribution reward because of the identified Gaussian noise in our equations. So since one random variable is Gaussian, the sum of all other random variables will be a new random variable, and also it will be Gaussian distributed. And also energy aware Thompson sampling algorithm by Kaufman, we did the same for it. What was our evaluation matrix? We have the average throughput discussed before. We have the energy efficiency, which is the average throughput over energy consumption per selected device in bit per second per joule. So this is the average throughput over the energy consumption during the time horizon. Also the average network lifetime, which is the time for the network where the energy of one or more of the nearby devices will be lower than the threshold level. Now, our simulation environment, we have 125 by 125 coverage area, and the devices are dropped randomly the millimeter wave channel assumption or channel formulation was utilized with the beforely mentioned blocking scenario. Here, the throughput against blocking density for EMOS, conventional and random. We mean by random that we choose one random nearby device. Also, from the figure, if we increase the blocking, the throughput is decreased, and this is already known. And also, the EMOS gives promising results. Also, the energy efficiency against number of devices for EMOS, conventional and random. The energy efficiency increased with the increment of the devices. And also, EMOS gives a larger result because it selects one device to do beamform training after investigations. Also, the energy efficiency against blocking density using 60 devices, and EMOS gives promising results. Also, the network lifetime against blocking density due to the effect of energy terms that we added to MOS equation, it saves a lot of energy for the network lifetime. Also, the convergence rate, which measure how fast or how speed the algorithm will be closed. Now the algorithm have near optimal convergence. The optimal here, we assume that we select the best nearby device from the first time. EMOS converges to about 98% of the ideal throughput. The same have been done for UCB family and Thomson sampling. This is the average throughput against number of devices, and this is the average throughput against the blocking at 60 devices. Also, the energy efficiency versus number of devices for UCB family algorithms and for Thomson sampling. And also, this is an energy efficiency against blocking density. And also the network lifetime and convergence rate. Now we will move to solution of neighborhood discovery selection using contextual bandits by making use of standardized communication devices, that any communication device have to be adaptable for the previous version. So any 5G device will be compatible with 4G device. So we can make use of Wi-Fi information of these devices as a context. So we formulated the problem by using contextual multi-armed bandit. We have the same assumption that the devices are quasi-static and their location is known by GPS service, but the blocking is unknown, and we assume that the device are dual band standardized devices using Wi-Fi. So the Wi-Fi information here will be the context. The context vector will be the received power, Wi-Fi power, and its mean and variance. This is the general contextual multi-armed bandit protocol. For each trial, we have to find the context vector that gives the information, and then upon the context vector, the algorithm will select the arm and get his reward, and the context vector will have a great effect to choose the best arm. The problem formulation is the same. We have to maximize the nearby device by selecting the best arm that gives us good or highest reward or throughput. Subject to this device have to remaining energy larger than limited energy. This is the definition of the throughput, and this is the spectral efficiency, and this is the Wi-Fi information. This is the context vector, and this is the received Wi-Fi power and its mean and variance. We leverage two famous Linus algorithms for contextual bandits, making use of the linear relation between Wi-Fi and millimeter waves. We leveraged LinUCB algorithm, which by Longley 2010, And we added the term, which is the distance over the remaining energy to the main equation of linear UCB to make it an energy-aware algorithm. And also the energy and the context is updated until we find the best R after the time horizon is finished. Also, we utilized a contextual Thomson sampling made by Agrawal at 2013 and added this term to it to maximize our reward using Wi-Fi information. Here, the simulation environment is the same like previous simulation environment, but we add the Wi-Fi information. Here, we leveraged the algorithms only without using the energy term to check the Wi-Fi information as a context effect. Is it good or not? So we compared the average throughput against the number of devices using contextual bandits and non-contextual bandits. And the contextual bandits give close performance or near optimal performance than non-contextual one. Also, the average throughput against the blocking density at 60 devices was checked. As the blocking increased, the throughput is decreased. And the contextual bandit gives also near optimal results and larger than non-contextual bandit, which means that good effect of Wi-Fi information. This is the convergence rate of average throughput or average reward against the reward. The contextual bandits have faster convergence than non-contextual one. Now we move to the other case, which is energy-aware contextual bandit against non-energy-aware non-contextual bandit. Here, the energy-aware linear UCB and contextual Thomson sampling gives higher results than non-contextual bandits. Also, for the average throughput against the blocking density, they give contextual energy-aware Thomson sampling and the UCB gives higher performance than traditional techniques and non-contextual ones. Also, for the energy efficiency, it gives higher results. And also for the energy efficiency against the blocking density, it gives higher results too. This is the convergence rate, which average reward or average throughput in gigabit per second against rounds. It also converges to about 98%. Now we will move to the other problem formula, which is unmanned aerial vehicle selection in disaster areas. Unmanned aerial vehicles are the drones, and it's important for commercial and military application. It can cover a lot of both disaster areas and the remote areas like forests, where the ground stations doesn't work or malfunctioned. Unmanned aerial vehicles can enhance the network caching to track them while users on also. And it can be on-demand flying base station as a one of a critical component for beyond 5G and systems. And also linking UAVs with millimeter wave will achieve these demands and user requirements. Our motivation here, we have a gateway UAV selection problem that with budget constraint, we leverage multi-agent or multi-player, multi-armed bandit to solve this problem using multi-agent battery-aware MOS and multi-agent battery-aware KLUCB with Gaussian environment. Multi-agent battery-aware MOS is well designed for stochastic and adversarial environments. Here, our system model, we have the disaster area where ground station doesn't work, and we have access UAVs. These access UAVs can have a specific area to investigate the rescues, and gateway UAVs that is on the borders of the ground area. Every time the access UAVs gather data and they fly to the gateway UAV, send it the data, and then the gateway UAV will fly to the closest base station working to upload the information. Now we formulated this problem as a multi-armed multiplayer multi-armed bandit with decentralized or distributed setting, where each player, the players are the axis UAVs, and the armies are the gateway UAVs, and the environment is a millimeter wave environment. Now the decentralized setting means, or distributed setting means, the axis UAVs will play the game selfishly and doesn't cooperate with each other to manage collisions that might occur. So both UAV will communicate with high-speed millimeter wavelength, and each axis UAV will target gateway UAV to maximize the data rate. Now the question is, what will be the reward? The reward, because we have a multiplayer, will be the total system or total sum rate. The received power, this is the millimeter wave linkage for UAVs. This is the transmitter and receiver, and this is the received power. We have M axis UAV and N gateway UAVs. The received power at the gateway UAV will equal to the transmitted power multiplied by the beam forming gains that depends on the beam width of the beams, multiplied by the path loss exponent. This is R, is the distance between the two UAVs, and eta is the path loss exponent. The problem formulation, we will try to maximize the total sum rate between the two UAVs, subject to there is a connection or a linkage between the two UAVs. And second, we have to update the information of battery consumption. Here, T is the time horizon, and rho H is the hovering time, and DH is the hovering duration, and rho F is the flying engine power, RF is the minimum distance between M and N, and VF is the axis UAV flying speed, and this is transmitted data length over the rate. Now the reward is the overall sum rate, which is the minimum between the rate of M and N, or the rate between the gateway UAV and the connected base station N. This is the rate is the bandwidth log to 1 plus signal to noise ratio. Now the multi-agent battery aware KLUCB gateway UAV selection algorithm. Here we added the term which reflects the battery consumption if we choose a specific M gateway axis UAV. And also this is the battery update information or update equation discussed previously. Also, we leveraged the same idea to multi-agent battery aware MOS gateway UAV selection. We added the term to the main MOS equation, and we update the parameters. Here, XMN is the number of times that the gateway UAVM has been chosen by axis UAVM up to time T. The evaluation matrices are the average total sum rate we discussed previously, and the convergence rate. Simulation environment, we will have 750 by 750 meters square, and we have gateway UAV radius. Now we have system rate against axis number using 20 gateway UAV and 60 beam widths. Also, the system rate versus gateway UAV number of 20 axis UAV and beam widths of 60. The algorithms of MOS and KLUCB gives promising results, especially MOS, because it's adapted for both stochastic and adversarial environment. Also, the average system rate against the beam widths between the two base station, the two axis and gateway UAV. Finally, the convergence. The algorithms converge at a few trials at 400, and also the convergence using 40 axis UAV and 20 gateway UAV with beam widths of 60. Our conclusions, multi-armed bandit have been leveraged to solve neighborhood discovery and selection problem, and for gateway UAV selection problem. The proposed techniques are promising solution with fast convergence. Our future work will include multiplayer, multi-armed algorithms for multiple devices, and we might extend the neighborhood discovery for vehicle to vehicle or adversarial environment. And also we'll investigate the map solutions for 6G problems like intelligent reflective surface and underwater communication and software-defined networks. Thank you very much.
Thank you, Sherif. Okay. In the audience, if you have any questions, please raise your hands. Then I can pick you up so that you can speak. And there was some question from the Q&A section, and I already answered by text. But the question is it true that Bandit
reinforcement learning
is more suitable than gradient descent? Sherif, can you comment it?
Yes, because Bandit is more applicable in real in the applications, because you have to try with the all armies and investigate the environment, not to take one arm and exploit it. So you have to trade off between exploration and exploitation, which is more realistic than exploiting something using gradient descent.
Okay, thanks. Maybe if you have any further question, maybe you can pose questions later.
Please send me any questions, and I would like to answer.
Okay. Then thanks again, Sherif. And Seihiro Sensei, could you show your slide?
Hello, everyone. I'd like to talk about multi-instance learning problem, which is based on Shapelet. Shapelet is a concept of local features, as briefly introduced by Hatano-san. And this work is collaboration work among 3 teams in AIP. And work has been already published in Neural Computation Journal. Okay, let's start. And let me introduce myself briefly. As introduced by Hatano-san, my main workplace is Kyushu University, and I work as an assistant professor. And my research interests machine learning theory and applications, such as machine learning reduction or generalization error bound. And applications are image recognition or some tough learning tasks. For example, learning with noisy data or weakly labeled data or imbalanced data. And so if you are interested in my work, please feel free to contact me. Okay, in the beginning, I'd like to talk about multi-instance learning problem called MIL. And here is the informal definition of MIL. In MIL problem, data is given as a set of instances, and each set is called a bag. This is a bag. And this is important. In training phase, the bag is labeled, but each instance is not labeled. And the typical goal is to find some rule to predict the label of unseen bag accurately. And so next, we show some simple example of MIL. For example, for image recognition task, for example, considering MIL is a standard approach for image recognition task, and consider leopard recognition. This is a leopard and a bear cat, such images. And the image set includes various animals. And in some cases, to consider local pattern. Local pattern is a good way for accurate recognition. For example, some ear or nose or eyes, or some textures. And so if we divide each image into small patch images, for example, 8 times 8 patches, and the image is considered as a set of 64 dimensional vectors. Then, as you can see, each image corresponds to back, and patches correspond to the instances. For example, leopard recognition, the positive back is a leopard image. And the typical prediction model is to score the maximum similarity between some local pattern and patches. And this local pattern can be obtained by learning a hyperplane using such as SVM-like algorithm. And for image recognition tasks, such local feature-based classification is sometimes effective. And next, let's consider more difficult case. If we have some ambiguous images, for example, some people wearing a leopard t-shirt, and in such case, it is very difficult to classify using a single local pattern. And we show typical approach using local features for such cases. The idea is very simple, just using multiple local patterns. That is, consider feature space based on the similarity with multiple local patterns, and then learning the hyperplane over the feature space. In this feature space, each dimension corresponds to the maximum similarity with some pattern. And the formulation is like this. But so the natural question is, how do we find these patterns? And in the previous approaches, just using all training patches is the most popular approach. But this is a heuristic approach. So the next, as shown in the presentation title, we introduce Shapelet. So as briefly introduced by Hatano-san, the actual Shapelet is a terminology of time series classification domains. And gunpoint data is a very famous data set for time series classification. And each instance is a univariate time series of hand motion taken by motion captures. And typical Shapelet-based time series classification has two phases. And first, we prepare the set of short sequences like this, called shapelets. And this is prepared in some way. And we compute the similarities between shapelets and its best matching location in each instance, that is, each time series. And so we can define this best matching similarity as local feature. And so we compute the similarities for all shapelets, respectively, like this. And so we can define the feature space, whose number of dimension corresponds to the number of shapelets. And in second phase, we find the classifier by using some learning algorithm, by using such as a decision tree or SVM. And so you can see some good shapelets are discriminated local patterns. And it is reported that the shapelet-based method is interpretable and achieves high accuracy in practice. So the same question is occurred. In this shapelet learning task, the main problem is how to choose good shapelets. And actually, in typical approaches, the shapelets are all subsequences appearing in training time series, or shapelets are selected some heuristical techniques. And you may already notice that shapelet learning is essentially same with MIL. That is, time series corresponds to a bag, and subsequences corresponds to instances. And shapelets corresponds to local patterns. But curiously, the relation between shapelets and MIL has not been discussed yet. This is actually an important observation in this work. Okay, let's get back to the main topic. My main question is, how do we find good shapelets or local patterns? And in the previous approach, problem formulation and algorithm are heuristically designed. And we cannot theoretically justify the heuristic approach using some selected patches or subsequences in the training sample. And we believe that the most straightforward way is to consider all possible shapelets, all possible local patterns, not selected, not heuristically selected. And by using the concept of shapelet to MIL, the previous approach is summarized like this. The first introduced approach is considered as a single shapelet-based method. And the second approach is considered as a more difficult case. This, which considering a more difficult case, is considered as a finite shapelet-based method. In this work, we consider possibly infinitely many shapelets, and informally formulated like this. And our main goal is to present the learning algorithm in which the selected shapelets are theoretically justified, not heuristically selected. And I will reveal these boxes. So here's the list of our main results. First, we formulate a framework for shapelet-based MIL theoretically, and we theoretically guarantee the generalization performance of our methods. And present an optimization problem and boosting best algorithm. And the optimization problem is tractable by showing the representer theorem. And it is important to note that our method is generally applied for local feature-based learning tasks. For example, image recognition and time series classification, or other standard multiple instance learning tasks. And our algorithm efficiently learns the shapelets and the classifier, even with considering infinitely many shapelets. And practically, the method achieves high accuracy for time series data and multiple instance data. Okay, here we show the formal setting and generalization error bound. And this is a formal definition for multi-instance learning problem. And the sample is given as a set of labeled bags, and each bag is identically and independently distributed according to some unknown distribution, D, over power set of instance space, X. And note that there is no assumptions for instance distribution. And the goal is to find a prediction function, F, with small generalization error. This is a standard multi-instance learning problem. And here we define a local feature more formally. We assume that similarity between each instance, for example, patches or subsequences, and shapelet. Similarity between instance and shapelet is defined by some kernel function, K, which is a dot product over Hilbert space. And then for shapelet Z, we define the local feature. This is a local feature H as a max of K about X, and it is equal to max of phi Z dot phi X over Hilbert space. And for some technical reason, we extend these local features like this. For any U in Hilbert space, we redefine HU as max of U dot phi X. It means that we consider every possible shapelets in Hilbert space rather than input space. And our final hypothesis set is a convex combination of these local features, HU. That is linearly weighted local features. And our hypothesis set is all possible combinations of all possible shapelets, as briefly introduced just before. And so it has powerful representation using the local features, but most concern is a risk of overfitting. And then theoretically, by evaluating the Rademacher complexity of this hypothesis set F, we can guarantee the generalization error bound of any hypothesis F belonging to the capital F. And Rademacher complexity is a measure for evaluating the overfitting risk of the hypothesis set. And we obtain the generalization error bound like this. We omit the proof in this talk for any hypothesis F belonging to capital F is upper bounded by empirical margin error plus this guy. And as you may know, the bound means the gap between testing error and training error. So if this term becomes smaller, the gap also becomes smaller. This is a happy case. So we can see that our generalization error performance has only logarithmic dependency on the number of all training instances. PS means the number of all training instances. It means the number of all patches or number of all subsequences appearing with the training sample. But this is only logarithmic dependency. It means that very large number of training instances does not significantly affect generalization performance. And moreover, this theorem justifies to use large margin classifier. Okay, next week, introduce the learning algorithm. And here's the optimization problem that we want to solve. And you can ignore the detail of the problem. And roughly speaking, the learning task is that we find the linear weights that gives higher weight for more important shapelet-based local features. And the main difficulty in this problem is that we need to solve with the constraints for infinite dimensional space. But fortunately, we can approximately solve this problem by using boosting technique if we design a weak learning procedure. And for easy understanding, we show the overview of our learning procedure, which is based on boosting. This is an iteratively update algorithm, and we iteratively update the sample weights and obtain the discriminative shapelet or shapelet-based local features for the sample weights. And in the phase of sample weight update for the current shapelets, we increase the weight of incorrectly classified data and decrease the weight of correctly classified data. Data means the back with the current shapelets. And for the current weight in weekly learning phase, we find the most discriminative shapelet. And for example, first we give equal weights for all samples and obtain the most discriminative shapelet or shapelet-based local features for the current sample weight. Sorry. And next, in the next iteration, we update the sample weight such that incorrectly classified data, this is ambiguous sample, incorrectly classified samples has larger sample weights, like this, and obtain the most discriminative shapelet for this sample weight. The weak learning problem can be designed like this, but there is a very difficult problem. The difficult problem is how can we find optimal U? It looks very difficult because the solution space is any points of Hilbert space. Actually, we can show the representer theorem, which holds, and U is represented as a linear combination of feature mapped training instances. And the weak learning problem can be described like this. And actually, this is a difference of convex programming and which is not convex program. But fortunately, we can obtain a local optimum using DC algorithm. And totally, the proposed problem is tractable, and we can learn a good combination of the shapelets and classifier efficiently. Okay, finally, we show the experimental results. First, we demonstrate our method using some benchmark data for multi-instance learning task, standard multi-instance learning task. And we used 5 popular benchmark data sets, MUSC1, MUSC2, and this is the molecule data labeled as MUSC or non-MUSC, and some images, feature mapped image data. And we compared with the previous Shapelet-based MIL methods, small MISVM and capital MISVM. And this is categorized as a single Shapelet-based method. And Miles is a finite Shapelet-based method, and this is a state-of-the-art performance. This achieves a state-of-the-art performance using the Shapelet-based local features. And we can see that our methods achieved significantly higher than small MISVM and capital MISVM. And Miles and ours are competitive performance. And we want to show the detailed comparison with Miles. We can see that in this table, the training accuracy of ours is basically higher than Miles. And it is actually natural that reasonable that because our hypothesis set has richer than Miles. And unfortunately, this means it means that ours has a higher overfitting risk, but on the other hand, ours has a possibility to achieve higher accuracy for more complicated data. And this is an important feature work. And next, we demonstrate our method for time series classification task. And we use the benchmark dataset, usual time series classification archive. Our method can be easily applied to multiple instance, multi-class learning problem, but I briefly introduced the tasks for binary level data. And I compared with the state-of-the-art methods, Shapelet transform and learning time series Shapelets. These are the state-of-the-art Shapelet-based methods for time series classification. And for time series classification task, our method achieved competitive performance with the state-of-the-art methods. The blue is our methods, and basically higher accuracy than state-of-the-art methods. And maybe STR, ours highly competitive, but significantly higher accuracy than LTS. But actually, ST consumes very high computational, is a very high computational cost, and ours is a very efficient. And we consider the Shapelets over Hilbert space, but we can keep the interpretability of the Shapelets by visualizing the matched subsequences with the Shapelets. And here are examples of the visualization. And we can easily see that which local patterns contribute to classify the time series. Okay, I conclude this talk. The main results are we formulate a framework for Shapelet-based MIL theoretically, and we derived a tractable optimization problem and present theoretical justification. for our methods. And actually, this is the this our theoretical result justifies not only our method but also the existing shapelet-based method using the training instances in the training banks. And we guarantee the generalization error performance. And the present boosting based learning algorithm, which is practically efficient compared with the existing methods, and achieve the high accuracy for time series data and multi-instance data. And the future work is to improve the generalization error bound or real-world application, or considering the relation with deep MIR approaches. And actually, I'm highly curious about the reduction to multi-instance learning problem. In this talk, shapelet learning task can be reduced to multi-instance learning problem. And I think that various kinds of learning problems can be reduced to multi-instance learning problem. And this is the actually ActX research project supported by JST. Okay, that's it. Thank you for listening.
Thank you, Seihiro Sensei. I think we have a lot of time for questions. From the audience, are there any questions? If you have any question, please raise your hand. Then, and also there was a question from Q&A, and I already answered a bit, but Seihiro Sensei, the question from the Q&A section was that, is it possible to apply the method to non-continuous in Hilbert spaces? Well, in my understanding, the listener is asking about Hilbert space, a kind of discrete Hilbert space.
For example, some strings or
yeah, maybe yes, something like that. So maybe our hypothesis space discrete.
Yes, I think it can be applied because we have no assumptions for continuous or non-continuous, and for some discrete target, we can apply the kernel function, and we can define the similarity between some discrete structures and some local patterns defined by some discrete structures.
Okay. So so even the formulation is based on a continuous space, but the actual solution is consists of training bugs, instances of in the bugs. So that's how discrete space can be dealt with. Is that right?
So this is the questions for this page, maybe. So yes, but yes, I think for discrete structures, by the result of representer theorem, we introduced in this page the discrete structures and corresponding this U is written as a samely written as a linear combination of feature mapped training instances, and training instances are discrete instances.
But let me see. So even if phi z in this page are discrete, phi z or z, but u is a, convex, a linear combination of phi z. So
Yes.
In if so, if u star has to be contained in the set, it has to be continuous.
Yes. Sorry. I think U is a continuous, not discrete.
But the original space can be discrete.
Yes.
Okay.
Yes.
Okay. Can you answer about the comment on the Q&A question?
Yeah. The question is that why I have never evaluated attention-based multiple instance learning. Attention is a very important local features. It is very attractively researched by some neural network communities, and of course, this is a very important concept for MIL. Attention-based MIL is a very important concept, but in my work, the main focus is to theoretically justifies the shapelet-based learning tasks, and shapelet and in shapelet-based learning tasks, the local features are defined by similarity between the maximum similarity between the instances and the shapelets. And so in this work, we only focus on the maximum operator for multi-instance learning tasks, but not attention-based concepts. So this is a interesting feature work. Thank you.
Okay, thank you. From the audience, do you have any other questions? If you raise your hand, I can pick. That seems okay. Okay, maybe we can accept questions later. And if you don't have questions now, let me thank Sensei again. Thank you.
Please feel free to contact me. Thank you.
Thank you. Okay, now then we have the final talk from Ryu-san. Ryu-san, are you ready?
Yes.
Okay, so then please share your slides.
Okay, greeting, ladies and gentlemen. Today we are going to introduce our research, improved algorithms for online load balancing. And this presentation is composed in 5 sections. Firstly, we introduce the standard load balancing problem, and same as the offline case. And then we are going to introduce our problem setting, the online load balancing. And in this section, we will compare our online load balancing problem to popular online learning problem, online convex optimization. And then to the key point of the method, we reduce online load balancing problem to Blackwell approaching game, and then to OCL game, and to OL game. And fourth, we deal with some implementation details. And at last, we give the conclusion and the future work. Well, let's come to the first part. Let's consider the offline case. Firstly, given a simple task with a unit size of data, like finding a particular IP address in a CSS file, then we can have a K service with load information represented as computing time per each unit size. And we can break the data down into K pieces so that each service can compute them in parallel, which can save the time of solving the total work. And for each survey, we give the size as alpha I from 1 to K. The strategy to minimize the running time is equalize the computation time of all servers. Equivalently, we want to minimize the mix span of our target. So we can summarize this problem in this form. The input is the running time for each service, and the output is distribution alpha. So our goal is to minimize mix span, like in this quotient. Of course, this is an optimization problem, and the solution is very trivial, that for each distribution is defined here from each running time is equalized. So we can also rewrite this problem with some useful notations as alpha O dot L with L infinite norm to represent the mix span, and the optimal choice here, we can denote them as C star with L infinite norm with respect to the loss vector L, or we also call them as load vector. Same. So now let's come to the online version of this problem. So the online load balancing problem with L infinite norm is researched firstly maybe 10 years ago by Eva Dan. So this problem is stated as follows: for each round T from 1 to large T, at round small t, algorithm firstly chooses a task assignment, alpha T, and then this algorithm observes the load information as a vector LD. But we need to pay attention that in online load balancing problem, algorithm should choose alpha T when LT is unknown. So this is a prediction problem rather than an optimization problem with the offline setting. So the goal of this algorithm is to minimize the regret, which is defined as the difference between the maximize of the mix span and to the statistical optimal choice. Maybe this formulation is so complicated, and we can rewrite it according to the rule in previous page that you can say this is like a global loss minimize optimal in global load information vector. Of course, our problem, we generalized the norm from the L infinite norm to a general norm with some assumptions. So this problem is stated as follows, but only difference is the regret definition is extended from L infinite norm to a relative generalized norm with two assumptions. The first assumption is that the norm is a monotone norm, which means that if each entries of the vector is bounded, and then the vector with respect to the absolute value, then the vector is bounded. And then another assumption is about the statical global optimal. It is supposed to be a concave function. Of course, this extension is reasonable as any LP norm is monotone norm, and therefore C star with this LP norm is also concave, and our extension naturally contains the L infinite norm. So now I want to do some comparison between our online load balancing with online convex optimization, because you know it's a very central topic of our research team. For online convex optimization problem, it's also like online prediction problems. It's also stated as follows. Firstly, player or algorithm chooses WT in the set W, and then adversary returns a convex loss function FT to the player, and then the player incurs the loss FT with in the chosen vector WT, and the goal is to minimize the regret, also defined as the difference between the simulative loss and the optimal choice with global loss vectors. And furthermore, if the loss function ft is a linear function, and we call this framework as online linear optimization. So naturally, we can have such question that whether we can just use the online convex optimization OCO paradigm to apply it in our online load balancing problem. But like in this way, that each round player first chooses the distribution alpha, and then adversary returns a convex function defined as alpha O dot L with respect to any norm, and then this is a loss incurred by the player, and our goal is to minimize the regret. Why we cannot use that directly, but unfortunately the answer is no. Main difference, at least we can say, is from the regret. The first line is the regret of OCO according to the last page, and the second line is the regret we defined for the online load balance. So obviously difference is, you can say, here is about the simulative loss here, and the global loss we will discuss for online load balancing problem. At least you can say the sum sign is outside of the norm or inside of the norm. So for online load balancing problem, we discussed it, the sign is inside of the norm, so we also call it as global loss. Now let's have a review of online load balancing. That at round T from 1 to large T, player chooses distribution alpha, and then adversary returns the loss of load LT. And the regret is defined with the global loss here, at least the sign is inside of the norm. And our goal is to propose an efficient algorithm where the regret is bounded by order T with power S, and S is smaller than 1, also called as sublinear. Here, efficient means that this algorithm is running in polynomial time for each round T. This is also an important point in our paper. Okay, we can compare our result with previous work. With online load balancing problem with respect to L infinite norm, Eva Dan gave a regret with order greater T time log K, and the running time for each round is order k. Well, it's polynomial time. And 2 years later, Huckling gives a more precise regress bound, 30 times log k, but the running time is inefficient, exponential with k. So our work combines both advantages of these two works. And our regret is the best one, and the running time is polynomial with k, while we use the second order co-programming and linear programming efficient algorithms in our algorithm per each trial. Well, and these two algorithms we will discuss later. Okay, now we come to the key point as our main method. Our reduction is 3 steps, from load balancing to Blackwell approaching game, and then further to online convex optimization and to separated online linear optimization. So I want to firstly introduce what is Blackwell approaching game. This game we can specify with a total ABRSD, where A and B are two convex compact sets for two competitors, and R is a bi-affine payoff function from AB to RC. S is a target set, a convex closed target set in RC, and D is a metric on RC space. And Black approaching game is also in a very similar way to online learning. For each round T from 1 to large T, player first chooses a vector AT in set A, and adversary chooses a vector BT in B. Of course, A and B can be different set. And the goal is to let the average payoff RT bar convergence to the target set, which means that the infimum S in S, the T with respect to the metric, is smaller than the convergence rate. And this convergence rate will converge to 0 when T goes infinite. Maybe this is a very abstract concept, and we can do an instant to know it better. This is an example for Black approaching game, like rock, paper, scissors. And from T1 to large T, player A chooses 4 options, rock, paper, scissors, with an extra option mighty, and player chooses only 3 options. So mighty is like cheating options which can beat all other options. And the goal is to propose a strategy for player A with respect to requirements. Firstly, the winning ratio is larger than 50%, and the ratio to use the mighty option is less than 1/4. Of course, we can rewrite this example in a standard Black approaching game, where A, B is defined in this way, and R is a payoff function. And this blue space is the target set. Of course, we use D as L2 norm for the metric. Okay. Okay, let's come to the main part of the adversary and our algorithm. We can say that the adversary of the online in online load balancing game, the player of online load balancing is not with the kernel is from Blackwell approaching game until to 2 separated OL game C1, C2 with some reduction parts in this age, and the adversary keeps the same. Okay, let's come to the first reduction from online load balancing to Blackwell approaching game. This idea is very trivial. We just identify the algorithm for online load balancing to Blackwell approaching game. And this idea is also used by Eva Dan, but he only examined the L2 norm, which having a relatively bad regret, square root of t times k. And you can say here A is the task function with the distributions, and B is corresponding to the load information vector. R is the payoff function, it's an R2K space, and S is the target set, which is defined here, and D is measure metric. And you say, as we mentioned, Eva Zhan only examined the L2 norm here. So our work is just extended his work. We just used a new norm metric we called as a combined norm in online load balancing. So the reduction is similar. Only difference is that now the target set is defined with the our metric, our combined norm, and the measure metric is respect to our combined norm, while the target set is respect to the original norm with any generalized norm. So there is a theory which shows that the regret of online load balancing is bounded by 2t times the convergence rate of the Blackwell game. So this is the first step. And then we need to find a way to give an upper bound of the convergence rate of the reduced Blackwell approaching game. So then we choose the second reduction part, mainly from the follows the results from Chinkin's work from Blackwell approaching game to OCO game. Of course, we need to have a review of what is OCO game. It's game between online game between player and adversaries. Only the loss vector is convex function, and the goal of the regret is defined in this way. But there is still two challenges. The first, we need to define what kind of the feasible set of player choose WT from W, and and what is kind of the transformation from WT to alpha T, and load information to the convex function. So what is convex function? It's received, and what kind of prediction it gives. Of course, we can see here in reduction part, the player of Blackwell game player is composed in two parts, OCO player and two reduction. In round T, firstly, the OCO player gives a prediction WT, and then gives a reduction transformation part R1, and transferred to alpha T to Blackwell game. And then Blackwell adversary of Blackwell game gives the load information LT. According to the transformation R2, it is transferred to a convex function, which is defined as here, FT here, and to the OCO player. Moreover, the feasible set for OCO player is defined in here with the dual norm of the combined norm in a unit ball. Then Jenkins' work showed us that using the regret of the load balancing problem is bounded by 2 times the regret of the reduced OCO game. Then let's come to the last part. We reduce OCO game to corresponding OL game and separate it to two simpler OL games, C1, C2. As we mentioned before, the online linear optimization problem, OL game, is very similar to an OCO game, only the difference is that the loss function is a linear function, which can be represented as a vector. So the regret is also defined with the difference between a simulative loss and the optimal global loss, optimal of the global received FD here. And the reduction is also shown in this graph. And the player of OCO is actually composed with two separated OLO player and two transformer. And of course, at round T, firstly, OCO C1 and C2 gives its prediction WT1 and WT2, and then they send it to the transformer R3. R3 composes them together and as the prediction of OCO to adversary. And adversary returns the loss function FT. After R4 transformation, R4, this FT is transferred as a subgradient G1, GT1, and GT2 to the OLO player. Here R4. You can see here. It's the subgradient of FT in point WT here. It's defined in here. And this theorem shows us that the regret of OCO is bounded by 2 times the regret of corresponding OL game. So we combine these 3 reductions together, and the main result is obviously that the regret of the online load balancing is bounded by 4 times the regret with reduced to OL game, reduced OL game. And for this OL game, we have EG plus minus algorithm, and it obtains the regret O with T times log K. So this is our regret for online load balancing with L infinite norm. The regret is bounded by square root of T times log K here. Well, then we come to some implementation details with respect to the efficiency. Our algorithm is efficient because not only the online OCO or OLO game is efficient, but also for the transformation part. There are 4 transformations part, and the rest 2 one is very trivial. And what we need to mention is R1 and R4, respectively for alpha T and the subgradient. For alpha T, it's very trivial that we can use linear programming. And for R4, we should use second order co-programming to calculate the subgradient of HSW here. Therefore, we can guarantee that our algorithm is efficient. Now, conclusively speaking, this paper showed us an efficient algorithm for online load balancing problem with respect to L infinite norm, and the regret norm is square root of T times log K. And we reduce online load balancing problem to Blackwell game, to OCO game, and OL game further to 2 separated OL game, C1 and C2. In the first reduction, we involved a combined norm, and in the third reduction, we used second order co-programming and efficient reduction to obtain the subgradient of FT, and we break the OLO game to 2 relative simpler game, OL game C1 and C2. And you see for the red arrow is our contributions in this paper. And there are some open problems for online load balancing problems left here, like whether we can find efficient algorithm for LP norm, T is larger than 1, not only infinite, or whether we can find some lower bound of the regret to online load balancing. Okay, thanks.
Thank you, Yu-san. From the audience, are there any questions? If you have any questions, please raise your hand and I will pick you up. Could you show me the last slide, the summary slide again? So the technical contribution correspond to red arrows?
Yes, red arrows.
Okay. What do you think which is the most difficult part? Or do you have any comments?
Well, personally speaking, I think to involve the combined norm is difficult to be sorted, to be considered. And the main contribution, say, in this paper is the second order column programming to calculate the subgradient.
I see. So clarifying the hardness of the problem is a hard part.
Yes.
Okay. Then, okay, let me thank Ryu-san again. Thank you.
You're welcome.
And there's a question from Q&A section. Is it easy to generalize to other tasks? Can you comment on that, Ryu-san?
Okay. I don't know what this generalize means. If you mean to generalize for the any LP norm, I think the difficulty part is to calculate the corresponding subgradient here. I think that's a difficulty part. Otherwise, it's not efficient.
Okay, so maybe for general norms, we can formulate similarly, but there's no efficient algorithm for that. That's the answer. Okay.
Yes. Yes.
I see. Okay. If there's no other questions, I'd like to advertise the next seminars. So these are upcoming AIP Open Seminars. It's held every Wednesday, the same time. And I think these talk will be very interesting. And finally, I'd like to thank very much the attendance listeners for attending this seminar, and any questions later are very welcome. So thanks again, and see you in the future, maybe at face-to-face. Thank you.